Hello, welcome to this NPTEL course on Introduction to the Application of Artificial Intelligence to Robotics. I am Pushparaj Pathak, a professor in Mechanical and Industrial Engineering Department, IIT Roorkee. So, in this course, we are going to integrate AI with robotics, and this course is divided into 12-week learning program, and in this 12-week learning program we are going to study the different aspects of AI and robotics. This course is basically segmented into 3 segments. The first one where we'll be learning everything about the basic concepts of robotics. In the second segment we'll be learning all the concepts of AI which are applicable to robotics, and in the third segment we will be looking at some of the experimental demonstrations. So the learning outcome from the today's lecture is to know about the course content, and we have to see the robots and different associated concepts with the robots. So in week 1, we are going to see all the introduction part. So it's a basically foundational week. So here I'm going to introduce the robotics and the AI. So we have one lecture dedicated to the introduction to robotics, another lecture on introduction to AI. Mathematical background is very essential in this course. So one lecture is dedicated on the mathematical background. Then we'll be seeing Python as a modeling and simulation tool, because most of the work here will be doing in Python, and at the latter part of the week I will be introducing robot operating system ROS, in which many of the simulations done. Next week, that is week 2, it is dedicated on manipulator kinematics and static forces in manipulator. So essentially here first we are going to see how can we represent a manipulator mathematically. So here comes the spatial representation and DS parameters. Then we are going to see the forward kinematics and the inverse kinematics of manipulators using examples. Then we will be coming to the concept of Jacobian singularity and the workspace, and at the latter part of this week we will be studying static forces in manipulators. So in week 3 we are going to study the manipulator dynamics, where initially I am going to introduce the acceleration of a rigid body and the mass distribution. Then we are going to see the Newton-Euler equation and an example of the based on Newton-Euler equation. Then we are going to see the Lagrangian formulation of manipulator dynamics, which is energy based, and finally in this week we will be seeing manipulator dynamic equation in the state space form. Okay, in the week 4 we are going to study the trajectory generation and the manipulator mechanism design. So here we will be seeing the trajectory in the joint space form and the Cartesian space form, and the manipulator mechanism design dedicated 2 lectures on that. So in the first lecture we will be seeing some of the basic concept, and then in the second lecture we will be seeing the implementation of those concepts, and in the last lecture we will be seeing an example of the design of the SCARA robot. The week 5 I have dedicated to the control aspects, where we are going to study the linear and the non-linear control of manipulator. Okay, so in that one we will initially begin with the linear control of manipulator, and then we will be seeing how can we model a single joint and how can we control that, and then we will be studying the non-linear and time varying systems and what could be the control problem of the manipulator, and then Cartesian based control scheme. Okay, so here essentially we will be taking a simple example of a simple spring mass damper system, and I will be explaining the basic concept from that. The week 6 is dedicated to the machine learning basically, and it's a idea implementation for say picking up an object, okay, and putting up the object. Okay, so initially we will be seeing the fundamental of machine learning. Okay, the 2 lectures are dedicated on that. Then what libraries and tools needed for machine learning implementation in Python. So that I am going to discuss here. Okay, so NumPy and other tools. Then introduction to decision tree and the random forest. These are 2 supervised learning models which we are going to study.
and I'll conclude this week with the reinforcement learning for the grasping of the object. In the week 7, we are going to see how does the robot identify an object. Okay, so essentially we are going to see the computer vision and its concept. Okay, so capturing up the image using computer vision, then how that image is processed, so that we will be seeing, and how can we extract the information from those images. Okay, those information which are useful for the robot to take a decision. So that we are going to study. Then I will be introducing the artificial neural network to you, and through advanced version of that, that is CNN, we will try to identify the object. Okay, and here I will be demonstrating that through the YOLO version 8 tool. In the week 8, we are going to see how we can put an object after grasping it at other place. So here comes actually the path planning aspect. Okay, so we are going to see the grid search as well as the A star algorithms. How do we avoid the obstacle when robot is moving, okay, following a path. And I am going to also introduce the deep reinforcement learning concept over here, and we will see how the GPS is used for the path finding. And towards the end of this week, I am going to introduce the fuzzy control concept to you, and we will be seeing that how we can use the concept of fuzzy for the mobile robot navigation. In the week 9, it is a AI based navigation which I am going to talk about. So here we will be seeing some basics of the genetic algorithm, okay, and then the genetic algorithm for path planning, and then implementing the neural network for the navigation purpose, and understanding of the perception, localization and mapping. So here some basic concept will be there, and then I will introduce the SLAM, okay, which is simultaneous localization and mapping, and the floor finding technique. In week 10, we are going to see if a robot want to interact with the human. Okay, so what basic things will be needed. Okay, so here AI based speech recognition and robot emotion that we are going to see. So I will introduce the natural language processing to you. We will be seeing the concept of transformers. Okay, so here we are going to see the concept of transformer, and then we are going to see the AI based speech recognition. Okay, and then we will be studying about conversational AI and the human robot interaction, and finally I will close the week with developing an emotion engine for a robot. So this week is dedicated to the HRI basically, where we will be studying all the basic concepts of human robot interaction. In the week 11, we are going to see the essential aspects of the hardware part. Okay, so we are going to see what all hardwares are needed in the robot. Okay, where we are going to see the actuators and the memory devices, okay, and other communication devices and all. Then we are going to study the sensors for sensing of the environment. Then one lecture is dedicated for the electrical actuators, which are mostly used in almost all the robots because their easiness in implementing the various control schemes. And then I am going to integrate the AI concept with the robotics. Okay. So although in our earlier lecture, wherever I found the opportunity, I have incorporated the examples of the robotics, but here I am going to talk about two things. One is relating the kinematics of the robot and AI, and the other one is relating the dynamics of the robot and AI. The week 12 is the demonstration week actually. So here we are going to see the demonstrations, okay, which we have created in our robotics and control lab of Mechanical and Industrial Engineering Department, IIT Roorkee. And these demonstrations we are going to show on a humanoid robot which we have developed in our lab, then one on the KUKA KR5, which is a industrial robot. Then a demonstration on ROS will be given. I introduced this ROS in the first week duration, but here we will be seeing it in much more detail. And then how this ROS could be used in mobile robots. Okay, so demonstration of AI in mobile robot, this we are going to see. And then I'll close this course with my last lecture on a short discussion on the application domains where we can use these course outcomes, okay, what ethics one should follow, what safety precautions we have to take, and what is going to be the future of AI robotics, okay. And then we'll be just reviewing the course which we have studied and what going to be the probable career pathways for all of you, okay. So that we are going to see, and how this is going to help you in picking up that career pathways. So that also we are going to see in this lecture.
With this, now let us start with our first lecture, which is the introduction to robotics. Okay, so you see, a robot is an integration of, say, mechanical part which constitutes the robot's body, then the electrical part where we have the actuation and sensing, and the software components which essentially try to control the robots, okay. And these software components can be reprogrammed to perform a variety of tasks, okay. It could be with human intervention and it could be without human intervention. Okay, so the robotics topic as such is the study of robot design, robot programming, and the control. And the word robot has its roots in the Slavic language, and which essentially means a worker or compulsory work or drudgery. The word robot was popularized for intelligent machines by Czech playwright Karel Čapek in his play R.U.R., okay, that is Rossum's Universal Robot in 1920. The first commercial robot was introduced in 1962, okay, and it was developed by the Unimation Incorporation, USA, which was founded by Joseph F. Engelberger, who is often called as the father of robotics, along with the inventor George Devol. Okay, and it was installed in the GM plant, General Motor plants. So here we can see the robot, that is Unimate robot, and here we have the sketch of the Unimate robot where the various degrees of freedom of the robots are shown, say for the rotary motion, for the vertical motion, and for the radial motion, and for the end effector here we have the wrist bend, wrist yaw, and the wrist swivel. If we look at the classification of the robots classified, okay, based on, say, mobility and the manipulation. In case of mobility, the main goal is to transport, okay, whereas for manipulation, where our main goal is to perform an action on the environment. So first let us look at the mobile robot example. So mobile robot again could be the wheeled robot or it could be legged robot. So mobility could be either through wheels or it could be through legs. So the wheeled robots are used for the flat surface, and whereas the legged one are used for the walking and running operation. Okay, so as we can see that the wheeled robot, because they are going to move on a flat surface, okay, so naturally they have larger speed, but walking and running robots, they move on uneven surface, so their speeds are less than that of the wheeled robots. If we look at the second category of classification, that is the manipulator. So manipulator examples, say a very popular industrial manipulator, say KUKA KR5, or say manipulator for, say, used in the surgical applications. Okay, so the medical robots, painting robots such as KUKA KR5. Okay, so here we have the interesting issues, say how much area it is going to cover, how we could plan the path of that, okay, and these industrial robots could be teleoperated and autonomous. There are other classification of robots, okay, such as the fixed or mobile one, then serial robot or parallel robot, then according to the degrees of freedom, okay, then we have the rigid or flexible robots, Then what type of control are we using, whether we are going to have the point-to-point control or autonomous and intelligent control. Okay, most older industrial robots were fixed base and consisted of links connected by actuator joints, and many modern robots can move on factory floors, uneven terrain, or even walk, swim, and fly. So let us look at this classification, that is serial or parallel. So this figure shows the serial robot where we have a fixed base and we have the various links which are connected sequentially and ending in a end effector. Okay, whereas in case of parallel robots, there are many number of loops and there is no natural end effector. Now, based on degrees of freedom, the classification also could be done. So, the degrees of freedom determines actually the capability of a robot and the number of actuated joints. Okay, so you see any object which is there in space, it has got the 6 degrees of freedom, right? So the 3 translational degrees of freedom and 3 rotational degrees of freedom. I hope all of you are aware of the definition of the degrees of freedom, which is basically that is the number of position coordinates, number of coordinates needed to specify the position and orientation of an object. Okay, so if an object is there in space freely, say flying, it has got 6 degrees of freedom, the 3 translational degrees of freedom and the 3 rotational degrees of freedom. Okay, so if I want a robot to do all say type of motion, it should have at least the 6 degrees of freedom. So 6 degrees of freedom are required for an arbitrary task in 3 dimensions. Painting and welding can be done with even less than 6 degrees of freedom, say by 5 degrees of freedom. The electronic assembly is usually done by 4 degrees of freedom SCARA robot. And okay, for extra flexibility and working volume, 5 or 6 degrees of freedom robots mounted on say 2 or 3 degrees of freedom gantry or wheeled mobile robot, that type of configuration is also possible. That is a manipulator mounted on a mobile base. Okay, so this mobile base could have say 3 degrees of freedom or it could have say 1-2 degrees of freedom. Okay, then the redundant robots can have more than 6 degrees of freedom, and naturally these additional degrees of freedom are used for avoiding obstacle and giving more flexibility to the robot. The arrangement of the first 3 joints, say in case of fixed serial robot, is classified Cartesian, spherical and cylindrical. Okay, so the motion described by Cartesian, spherical or cylindrical coordinates, based on that this classification could be done. And if we have human arm like look is there, so that we call as the anthropomorphic robot. Okay. Then the SCARA which I just spoke, or selective compliance adaptive robot arm, this is very extensively used in the electronic assembly. And the last 3 joints of a forms the wrist. Okay, and these are used to orient the end effector. Coming to the rigid versus flexible robot classification. So here is the example of the rigid robot and here is the example of the flexible robot, which are used, flexible robots which are used for the space applications. Okay, so these most of the industrial robots built to be heavy and rigid so that we get the required accuracy, whereas minimizing weight for space applications, that is our target. So links and joints are made flexible in that case. Then other classification could be control and mode of operation. Okay, so most older industrial robots were teach and playback type. Okay, so these robots, so in this one what is done is that the robot is taken manually through the task and positions are recorded, and then during actual operation the robot plays back those taught sequences. Okay, so very time consuming this way of doing is there, very time consuming to teach, and robot cannot react to any changes if there are any changes in the environment. The other type of control could be the computer control. Here inputs are given from the computer, often being tried out in an offline programming environment. So I'll be discussing much more details about offline programming environment during later part of this lecture. Okay, then the control could be sensor driven. Sensors are used to say avoid obstacle and take decisions. Say we could use IR sensor or other sensors for that purpose. Then the intelligent control, where robot can learn about the environment using AI and perform efficiently. So there were three basic laws of robotics which were introduced by Asimov. So there were so many apprehensions in the mind of people when robots were introduced. So Asimov introduced these three laws. The first one is that robot must never harm human being. Okay, and the second law is that robot must follow instruction from humans without violating rule 1. Okay, and the third one is that robots must protect themselves without violating the other rules, that is rule 1 and 2. Okay, summary of this is that the robot should perform the task as defined by the user, and they should not harm the human being, as well as they should not destroy themselves. Okay, so let us go a little deeper into this lecture. So in robotics, essentially our task is to handle the object. Okay, so when we want to handle the object, okay, essentially we need to understand the mechanics and control of manipulator. Now here, when we are handling an object, we should know the location of the object in the three-dimensional space, right? Where the object is located and how it is oriented basically. So the object can be described, the object in the environment, say here, they can be described by two attributes. One is the position and the other is the orientation. Okay, now to describe the position and orientation of a body in space, what we do is that we always attach a coordinate system, as you can see over here. So we always attach a coordinate system or frame rigidly to the object. Okay, and this frame can serve as a reference system within which we can express the position and orientation of the object. Okay, so transforming or changing the description, these attributes of a body from one frame to another frame, that is of course needed. Okay, then coming to the kinematics of manipulator, as all of you know, kinematic is the science of motion that treats motion without regards to the forces those are causing the motion. And here in kinematics, we study basically the position and its derivatives, okay, which are velocity, acceleration, and other order derivatives, okay, and naturally these derivatives are position with respect to time. Okay, so here basically our aim is to study all the geometric and time-based properties of the motion. Okay, and a manipulator consists of, as I defined in the earlier slides, nearly rigid links which are connected by joints that allows relative motion of the neighbor links. So here we can see we have the manipulator which is shown here. This is the end effector. Again, I am indicating end effector. I can indicate the position and orientation of end effector by fixing a frame to it. And here is the base frame or the inertial frame. These are the joint rotations, theta 1, theta 2, theta 3. So these joints are usually instrumented with the position sensors. Okay, these could be your potentiometer, or it could be your encoders. Okay, and this allows the relative position of neighboring links to be measured. Okay, and case of rotary or revolute joints, these displacements are called the joint angles. And some manipulator may have a sliding joint which we call as a prismatic joint. Now, coming to one of the popular terminologies used in the manipulator, that is the forward kinematics of manipulator. So basically, I said a manipulator consists of links which are joint using different type of joints. Okay. So in the forward kinematics, what we are trying to do is that we are trying to find out the position and orientation of the end effector, okay, if we are giving the joint angles. Okay. So for given set of joint angles, the forward kinematic problem is actually to compute the position and orientation of the tool frame or my end effector, okay, with respect to the base frame. This is the base frame. Okay, here essentially what we are trying to do is that we represent the manipulator position from the joint space, that is from joint angle to the Cartesian space. Then in the inverse kinematic of manipulator, we are trying to do the reverse. Okay, that is we are given the position and orientation of the end effector and we try to evaluate the joint angles. Okay, so this concept is very much useful in robotics because we usually know the object which has to be handled, and say if we know the position and orientation of the object, then our task is to calculate these joint angles so that that object can be gripped by the end effector. Okay. And there is a problem, and that problem is that the kinematic equations are non-linear and their solution is not always easy, and it is even not in the solution is not in the closed form. Okay, there could be questions even also whether a solution exists at all. Okay, or there could be chances that we have the multiple solution for that inverse kinematic problem. Okay, so the existence and non-existence of a kinematic solution actually defines what we call as the workspace of the given manipulator. It's basically the volume up to which the manipulator can reach. That maximum volume is what we call as the workspace of the manipulator. Okay, and the lack of solution means that manipulator cannot attain the desired position and orientation because it lies outside the manipulator workspace. Okay, then next we will be looking at the Jacobian of the manipulator, and it essentially defines a mapping. Okay, it defines a mapping from velocities in the joint space to velocities in the Cartesian space. Okay, so this is how it is defined. So here say these are the joint velocity vector, and here we have the Cartesian velocity vector. So this is the Jacobian, which essentially defines the mapping from the joint space to the Cartesian space. Okay, so it could also define, that is mapping from the desired contact force to the torque required to generate them. Okay, so here also the Jacobians comes into picture. Now here there could be certain points of what we call as singularities where this mapping is not invertible. Okay, and understanding of that phenomena is basically important from the designer's perspective, the designer who is going to design a manipulator. The most important part in any manipulator is the dynamics. And the dynamics is devoted to studying the forces required to cause motion. Okay, now as joints accelerates, okay, that is joint accelerates, or we say that the manipulator starts from rest, glide at constant end effector velocity, and finally decelerates to a stop. Okay, so in this entire operation, a complex set of torque functions must be applied by the joint actuator. Okay, so the exact form of the required functions of actuator torque depend on say spatial and temporal attributes of the part taken by the end effector and on the mass properties of links as well as that of payload. And apart from that, not only this, the friction of the joints, okay, that also affects. Okay, so one method of controlling a manipulator is to follow a desired path involving calculating these actuator torque functions by using the dynamic equations of motion of the manipulator, which we will be seeing. So, the dynamic studies of force required to cause the motion. Now, there could be two applications for that. Okay, so one application is that we calculate the torque required for the desired motion, which we call as the inverse problem. Okay, and the other could be, that is the direct problem, could be that we find acceleration in terms of the torque and then calculate the displacement. Okay, so this is what two types of study we do in the dynamics. Next part is the generation of the trajectories. Okay, so if end effector has to move from path point A to point B, okay, say one must compute a trajectory each joint has to follow. Okay, so what should be trajectory of these joints when the end effector has to move from point A to point B. Okay, so commonly each joint starts and ends its motion at the same time, so the manipulator motions appears coordinated. Okay, often a path is described not by a desired destination but also by some intermediate locations, or what we call as the via points, through which the manipulator must pass en route to the destination. Next, we will be looking at the manipulator design and sensors. So, manipulator design, naturally the economics govern it, what type of manipulator we are going to design. So, there are factors such as size, speed, load capability, number of joints and their geometric arrangement. These things are to be considered. Now, these considerations impact, of course, the manipulator workspace size and the stiffness of the manipulator structure. Other issues are the where we need to locate our actuator, where we need to have the transmission systems for transmitting power from the actuator to the joints, and the internal position and the force sensor. So, the design of mechanical manipulator must address issues such as the choice of actuator, the location of actuator, the transmission system, structural stiffness, sensor location and more. The more joint of a robot arm contains, naturally more dexterous the robot is going to be. Okay, and again there is going to be a problem. If your robot is going to have more joints, naturally you will be requiring more actuators, more sensors, so it will be harder to build as well as it is going to be more expensive. To make a robot useful, there could be two approaches. Okay, the first approach could be that we built a specialized robot for a specific task, okay, as per the requirement given by the user. Or the other approach could be that I make a universal robot, okay, that would be able to perform a variety of tasks. Okay, so in case of specialized robots, some careful thinking will yield a solution for how many joints we are going to have. Okay, so for example, say specialized robot design especially for say electronic assembly on a flat circuit board does not need more than 4 degrees of freedom, right, or the 4 number of joints. Now, 3 joints allows for the hand to assume any position in 3D space, and the 4 joints allows the hand to rotate the grasp component about a vertical axis. Okay, and for the universal robot, the fundamental properties of the physical world we live in dictate the correct minimum number of joints. Okay, that is, as I said, a minimum number of joints, that is 6, because any object in space can maximum 6 degrees of freedom. Then coming back to the linear position control. So, any robot, if we want to control, the easiest and simplest way is to have the linear position control. Okay, so some manipulator are equipped with say stepper motor or other actuators that can execute desired trajectory directly. Okay. However, most of the manipulators are driven by actuators that supply force and torque that will cause the desired motion. Now, in this case, algorithm will be needed to compute how much torque is needed for the desired motion. Now, here the problem of dynamics is central to the design of such algorithm, but that doesn't constitute a solution. Okay, so the primary concern about the position control system is to automatically compensate for the error in knowledge of the parameter of the system and suppress the disturbances that try to perturb the system from the desired trajectory. Now, to accomplish this, position and velocity sensors are monitored by the control algorithm which compute the torque component for the actuators. Control algorithm synthesis may be based on the linear approximation of the dynamics of the manipulator. Okay. Now, in order to cause the manipulator to follow a desired trajectory, a position control system must be implemented, and such a system uses feedback from the joint sensor to keep the manipulator on the course for motion from, say, this point to this point. Then little complicated type of control is the nonlinear position control. Here, the control system based on approximate linear models are popular in the current industrial robots, but the nonlinear dynamics of manipulator, if considered during control synthesis, it is going to give naturally the better performance. There is another concept what we call as the force control. Whenever an object is being gripped by the end effector, we would like to have the force control on that. Okay, so the aim of the force control is to control forces when manipulator touches parts, tools or work surfaces, and the force control actually complements the position control. So when the robot is moving in the free space, we have the position control, and when the robot comes in the contact, we have the force control. Okay, and since a manipulator is rarely constrained to move in all the directions simultaneously, we have a hybrid control problem. Okay, that is, some direction are controlled by position control law, and some direction and the remaining directions are controlled by the force control law. In order for a manipulator to slide across a surface, for example over here, while applying a constant force in this direction, okay, and sliding over here, okay, we need a hybrid position force control system. Okay, so this type of example could be, say, washing of your window. Okay, so when a robot is washing a window, naturally we need to have a certain force in the direction perpendicular to the plane of the glass while following the motion trajectory in the direction tangent to the plane. Okay, then coming to the programming of these robots, a robot programming language serves as an interface between the human user and the industrial robot. Robot manipulator differentiate from the fixed automation by being flexible, which means naturally the programmable. Okay, so what we do is that in offline programming system, the robot is programmed in the environment, okay, and this environment is usually created using computer graphics. So we program the robot using the virtual environment and then test whether that program is working properly or not, and then we transfer that program to the actual robot. Okay, so a very common argument raised in favor of this way of offline programming is that it will not cause production equipment to be tied up when it needs to be reprogrammed. Okay, so hence automated factories can stay in production mode for a greater percentage of time. Okay, and of course they take help of the computer aided design database for doing this type of activities. Okay, so the desired motion of manipulator and end effector, desired contact forces and complex manipulator strategies can be described in the robot programming language. Okay, say for example here we try to tighten a screw in this object. Okay, so the offline programming system, as you can see over here, so we do the offline programming over here and then we transfer this program, offline program, to the robot console, and the robot executes this task. So here are the references. First one is the textbook by J.J. Craig, Introduction to Robotics, Mechanics and Control. This I am going to use. First part, that is robotics part of the lecture, and the other one is another popular and recent book by Grover. It is on the artificial intelligence for the robotics, and the last reference book is written by me and my colleagues on the intelligent mechatronic system. Okay, so these are the broader textbooks. For the individual lectures, I'll be giving the references separately in that lecture itself if anything more is needed. Thank you.